Algorithms are the recipes that computers follow in order to solve problems. And as we seek to analyze ever larger data sets, we need very fast algorithms to process all this data.
Professor Kyng's group has created radically faster algorithms for many computational problems on networks. We can find network structures everywhere. Think of internet traffic, transportation, logistics, social ties, and physical systems such as electric grids, or even heat flows through physical material. Two important examples of the group's work include efficient software for understanding electrical flows in networks of resistors and theoretical algorithms for logistical problems, like planning cargo trains to route goods through a network. As theoretical computer scientists, the group begins by formally proving that efficient algorithms exist using mathematical models and formal analyses of the algorithmic process itself. When this succeeds, the group works on turning these theoretical algorithms into practical, useful software.
Yes, this two-stage process has been very useful. Stage one is to design an algorithm that provably scales well, but without worrying whether it works well in practice. And then stage two is to try to discover a simpler algorithm that truly works well in practice.
Consider the problem of electric flows. A theoretical breakthrough in the early 2000s showed that electrical flows could be computed quickly, at least in theory. Yet usable code remained elusive. How can this be? The breakthrough algorithm of the 2000s had the property that as the network size doubles, the time spent computing the flow roughly doubles. This is much better than traditional methods, such as Gaussian elimination, where the time grows by a factor 8 when doubling the input size. But the 2000s breakthrough algorithm is impractical. Even running it on a tiny network with a handful of nodes would take decades. Professor Kyng uncovered simple, practical algorithms and proved why they work using random matrix theory that originated in quantum mechanics. This algorithm both has excellent scaling and it runs quickly on real-world data sets.
Back in 2022, we achieved a breakthrough. We can now solve a huge range of problems in time that scales almost linearly in the problem size. We were focusing on assignment and logistics problems that are fundamental to computer science. Things like matching workers with jobs, or matching taxis with riders, or routing digital traffic. Together with collaborators, we introduced a new framework that merges gradient descent methods with novel network data structures, and this led us to much faster solutions. And now we're working on turning this into powerful real-world tools that people can use.